Okay, hello everybody. I'm very excited to introduce our distinguished panel of speakers for today's talk, which is going to be on the topic of AI RAN and Open RAN, exploring convergence of AI native approaches and future telecommunication technologies. And we're extremely lucky to have a great team of experts in this space. We have Pedram Johari, who is Principal Research Scientist at the Institute of Wireless Internet of Things at Northeastern University, where he has done extensive work on wireless and low-power communications. He previously served as research assistant professor with a by-courtesy appointment at University of Buffalo and chief technical officer of an IoT tech startup. We have Salvatore who is a research assistant professor with the Wireless Internet of Things Institute. He's previously served as visiting researcher at University of Paris and at Ohio State University. His research interests focus on network slicing and virtualization technologies for 5G systems and beyond, physical layer security, and AI and machine learning for networking applications. And we have Michele Polese, who is a research assistant professor at the Institute for the Wireless Internet of Things, Northeastern University, who has previously visiting researcher at New York University and AT&T Labs. He has contributed to numerous ORAN technical specifications and submitted responses to multiple FCC and NTIA notice of inquiry and requests for comments, and is a member of the Committee on Radio Frequency Allocations of the American Meteorological Society. So we're very lucky to have them here today. Before we start, we wanted to also mention that the networking channel is not just one event. It is an ongoing series of events happening every 2 weeks. 2 weeks from now, we will have a special event, which is going to be a fireside chat with Amin Vadat, hosted by Nick McCune, on the topic of networking in the era of warehouse computing and AI. So that should be really exciting. And with that, we're going to start for today. We're planning to make this an informal discussion to try and make it interactive. You, the audience, can help us out by asking questions. There's the Q&A feature at the bottom of the screen. If you would like to enable closed captions, you can do that. There's a button at the bottom of the screen. There's also a button to transcribe the text from English into the language of your choice if you would like to do that as well. So with that, I'm going to turn things over to our first speaker, Michele.
Yep.
You can feel free to proceed. Thank you very much.
Thanks, Matt, for the introduction, and thanks everyone for joining this. So the idea for the sessions today is to give an overview of some activities that are happening in the area of AI, AI and RAN, and Open RAN networks. Starting from the starting point is some of the research that we've been doing at Northeastern, and but the idea is that the more questions you're going to ask, the happier we'll be, so that we can discuss more and make this as interactive as possible. So please feel free to ask questions, and we can take them during the presentation or at the end during the Q&A. So just to give a little bit of introduction for everybody. My name is Michele Polese. I've been working at Northeastern since 2020, and we recently started this effort that is called Open6G, which is both a project funded by USD and in general more a center that is trying to connect several activities around open and programmable intelligent networks, especially on the wireless and cellular side. So we've been working on a vision to define, create, deploy, and experiment with open programmable and intelligent networks in several areas that go from the algorithmic research, which is shown in the more in the right part of the slide, touching on security, spectrum sharing, energy efficiency, and various use cases which are of interest to the community, and going to toward the left, working more on software, protocol stacks, architecture, testbeds, and so on. We've been doing this with a number of partners, including, for example, Open Air Interface and the Open Air Interface Software Alliance, to push forward open and programmable cellular system, beside many of the other industry partners And primarily the activities have been focused around three main areas. One is the more traditional research and development activities. We've been doing research in Open RAN, in cellular networks, developing proof of concept. So one thing that we try to do is to deploy networks which are complete end-to-end, which come with all the bits and pieces that you need to make a real network work, and try to transition the research that you do into these systems. The second area that has started a bit more recently is focused on testing and integration. So we have, if you're familiar with the concept of ORAN, there are entities within the ORAN Alliance which are called OTICs, which can certify and test equipment for its compliance with the ORAN architecture. And then we also been doing some system integration activities focused on, especially on optimization, end-to-end deployments and design of private networks. And so this is just to give a brief introduction on the center and the activities that we do. And you see also a presentation later from Pedram Johari on some of the more research-related activities that are part of the focus here. In the next few minutes, I'll just try to touch upon a couple of topics that we've been looking at in the area of openness and programmability for next generation wireless systems. And go from, so this slide describes a bit the vision from a research point of view, and I'll give a couple of examples of studies or developments that we've been working with together with consortia like the ORAN Alliance and the AI RAN Alliance. So the way we see and interpret programmability in next generation wireless system starts from the role that software, cloud, and AI play in cellular networks. We see them as a way to rethink how cellular systems are deployed. So combining software to drive the networks, cloud, and especially the automation that comes with cloud components, and AI, we think and we have been designing and deploying blueprints for intelligent multi-vendor, interoperable and agile Open RAN architectures. This graphic at the bottom of the slide shows part of this blueprint, primarily focusing on the RAN components. So we using the OAI, CO and DU stack with either commercial radios or USRPs. And a lot of work that we've been doing is extending these protocol stacks with open interfaces that enable automation and optimizations. The main novelty and innovation that I think the ORAN architecture and the overall open and programmable ecosystem introduces is the capability to effectively exercise AI-driven control and optimization on these systems. So basically exposing a network status toward these components, which are called RAN intelligent controllers, and deploying in a closed loop configuration and services on top of this stack. And this provides a practical way to basically enable intelligent AI solutions for a number of use cases that go from spectrum sharing and spectrum management, slicing and coexistence of services, mobility management, infrastructure, not only spectrum sharing, but also infrastructure sharing and dual use networks. So the idea is to, again, use software, cloud-based automation, and AI to rethink and redesign how cellular networks are deployed. So just to make sure that this is something that does not just remains in the lab and it's not just something that is published, but has a limited impact. We've been working with a number of consortia, and specifically here I'll highlight the Oran Alliance and the Iran Alliance in the next few slides, to transition this research into either specifications or technical documents that at the end transition to real world systems. I'll just make a couple of examples of this, and I'll take the chance to introduce also the AI Run Alliance, which is a bit a newer effort and something you may not be familiar with. So the iRun Alliance is looking at a fundamental question, which is that of how can we practically enable AI in wireless system. There is definitely a lot of interest in research on AI for improving wireless networks. So that's something that has been going on for a while. There's definitely research, and also the 3GPP has started some efforts for the standardization. There's also, so this is from the technical point of view, there are also some market and business drivers that are kind of motivating why several operators and vendors are looking at AI as something that can help from a business point of view, especially if you compare the traditional base station market with the AI and application market. And so these two motivations have led to the creation of this alliance, which is called the AI Run Alliance. On the top right, you see the founding members of the alliance, but now we've had more members joining, and the activities of the various working group of the alliance have started. The activities are those that are summarized here. So it's organized primarily in 3 working groups, but look at different uses that can be done combining AI and radio access network. So AI and RAN is looking at how we can create a network architecture that allows to share AI and RAN workloads to improve the utilization of the assets available to the operators. AI on RAN is looking at how can the RAN enable new AI application, for example, at the edge, and so on. And finally, AI for RAN is looking at how AI can enhance the RAN. So this is the more traditional use case of applying AI to the RAN to improve the spectral efficiency. So this is the first of the two entities and alliances that I wanted to mention. The second one is the Oran Alliance, which you may be more familiar with. And the Oran Alliance has been defining a network architecture that enable closed loop control and interaction from programmable elements, the RAN intelligent controllers, to the RAN protocol stack. So the work that we've been doing with some of the work that we've been doing with the Oran Alliance has focused on further extending this closed loop control domain into the real-time domain. So if you look at this diagram, the components at the top, so application for in the no real-time scale are apps, and application in the near real-time scale, like subs, are part of the current Oran architecture. So something that we've been doing is looking at how to extend this into the real-time domain. Extending it to the real-time domain, but not only that, also extending it to having some interaction with the user plane of the RAN. So the Oran architecture right now is primarily looking at how the control plane can be optimized and exercised through the Oran components. We think there's a chance to take a step further and also interact with the user plane in a more direct way. And in this sense, this new architectural component that we propose, that we call dApps, is something that can play the same role of for example, programmable languages for network switches like before, compared to the SDN, which is more focused on the routing of the packets. So we've been working with the Honor Alliance to transition this research on real-time control and user plane extension of the Honor architecture to the broader group. And today, the Alliance has published the first research report on use cases and requirements. All right, this I think is more or less like a very high level and brief overview that I wanted to give on how we have been working on this topic at this convergence of run, open run, and AI run to basically go from networks which are static, monolithic, non-programmable to networks which are more open, intelligent, and programmable. I'll hand it over to Salvatore from ZTouch Networks, and then we will be happy to discuss further later on. Salvo, you're muted.
Right.
Just
yes, I'm trying to find the right. I think this one should be the right one. Can you all see my screen?
Yeah.
Okay. So, first of all, thanks for the invitation and having us today. Again, I'm Salvatore. I'm one of the, I wear two hats. So one is research associate professor at Northeastern University. And actually from there, we founded a startup. It's called ZTouch Networks. I'm one of the co-founders. And one of the products that we are developing, we are commercializing, we like to describe it as an AI-based operating system for cellular networks. And today, I would like to kind of go over some of the problems and challenges that are related to integrating AI in Open RAN networks, but in general, in next generation networks. Because I think that the problems that we are facing now is that everyone is super excited about being able to start integrating AI in cellular networks. However, this comes with a variety of different challenges, and I'd like to go over some of these challenges and kind of explain exactly how we are tackling those, and even addressing some open issues, which probably have been only partially addressed in the literature or in general in the commercial space, kind of trying to stimulate the discussion on what are the research focus and that have not been addressed fully, and so probably kind of trying to stimulate where research should go. And so this is a diagram that probably you've seen several times, and I want to kind of go over. I will start with this slide because I think that to understand exactly why AI in cellular networks has different challenges, where we need to understand exactly where the AI is being used, how it's being used, and what are the different components that are being considered when using AI in cellular networks. So Michele gave a very nice overview of what are the different AI problems that you can kind of consider in ORAN. We have seen that there are RAPs, XAPs, and dApps. Again, RAPs are taking control of policies and decisions that happen in the non-real-time domain, usually at scales over 1 second. XApps take decisions at a higher granularity from 10 milliseconds to 1 second. And then dApps are actually bringing AI at the edge, taking decisions in the 10 milliseconds range. And as you can imagine, you have all these different AI loops that are taking over run control, not just control, but I would say inference in general, because you can do prediction, you can do classification. But I would say that the biggest challenge in this domain is that how to orchestrate and coordinate all these different AI models that are taking decisions independently. It's the challenge. And the reason is that so far, when you look at traditional cellular networks, most of the intelligence is taken by a few applications. Most of the time, they are centralized. For example, you have the SON, self-organizing networks module, where there are hosts, you host several network functions and they take decision pretty much for the entire network in a centralized way. And usually they're not very fast. But the idea is that you want to have control over the network. You don't want to change configurations too frequently. So you want to have some sort of centralized control of the network at very long time scale. Now with O-RAN and Open RAN, we are moving towards real-time control. We are talking about milliseconds. So we have AI agents taking decisions so fast, and this is completely different from what the industry has been used to so far. So there is a new challenge, which is how do we orchestrate and coordinate these different AI models? So I will say that in general, the problem of orchestrating intelligence in O-RAN is it's definitely a new problem. There are some studies in the literature. There are some white papers from industry trying to understand exactly what are the challenges, how to address them, and how the O-RAN alliance should create specifications that try to simplify the way AI and ML is being orchestrated and is being managed in Open RAN. I would say that if you look at the problem from a very high-level point of view, usually you have operator. The operator has intents. For example, they want to minimize latency, reduce energy consumption, and allocate spectrum optimally. This is usually the intent that they have. They don't have optimization problems, like they don't just write equations. They just have high-level intents. And most of the time, they just want to express them in a human language. And there are some efforts, for example, from the TMF forum on how to create representations of intents, which are still human-friendly, but they are representative so that machines can understand them. Then you have an AI ML catalog, and this is where you store all the XApps, the RApps, the dApps, all of your fancy AI models that are doing magic. And then you have the infrastructure. So you have these three different components. You have intents, you have a catalog of AI solutions, and then you have the infrastructure that needs to be controlled and monitored to satisfy the intent. And ideally, what you want to do is going into the AI catalog, select some AI models, and then deploy them so that the infrastructure adapts to the intent. However, how to achieve this seems easy, but it's extremely hard. And I will say that there are 4 different steps that we need to consider in this domain. The first one is understanding what the intent means exactly. This is one of the most challenging parts, because the intent, if you look at the intent, it's very high level. You're just minimizing latency, reducing energy consumption, allocating spectrum. However, this intent needs to be mapped exactly to the infrastructure. So you need to have some mapping feature and mapping function that no matter what infrastructure you're using, which can be completely different, imagine different topologies in different areas of the city, in different cities as well. The intent, it might be the same, but the infrastructure that is below, the physical infrastructure is different. So the intent is abstracting the infrastructure, but then you need to project towards the infrastructure as well. So how to map the intent into the infrastructure and how to convert that into something a machine can understand is challenging. The next challenge is you have these AI models and in a catalog, but if you look at what O-RAN will look like in a few couple of years, this will look like an app marketplace. So you will have like thousands, hundreds of different applications. They can be probably trying to do exactly the same thing. Imagine like 100 applications controlling network slicing, 1,000 applications reducing energy consumption to satisfy throughput requirements. They're all doing pretty much the same thing. What is different is the way they do that. So they might be like an XApp that minimizes latency, and then you can have an AirApp that minimizes latency and minimizes energy consumption. So if you have an intent, what's the AI model you have to select? And this is another challenge. Then the other problem is once you know what's the AI that you want to deploy, then the problem is where do we place this AI model? If we want to minimize latency, do we deploy an XApp? Do we deploy an AirApp? Do we deploy a dApp? So locating and kind of like placing the AI is another challenge because the performance of the network will depend on where we place the AI. Because where we place the AI, as I'll show you later, will determine which data you have available, how frequently that data will be available, and what are the control actions that the AI can take, and at which speed and frequency. And this will determine how much the performance improvement you can get from the AI model deployed on your infrastructure. And then we have a merely, let's say, engineering problem of how to deploy the AI. Thanks to, I would say that this step probably is the I'm going to say the easiest one. It's not easy. I'm just saying the easiest one compared to the other three, because the other specifications now specify that if you want to deploy AI in general intelligence, you need to deploy that as accepts, RApps, or dApps. So there is already a packaging. And there are interfaces on how to deploy this AI. So in general, this last step is something that the ORAN specifications cover pretty well. At ZTouch, we have developed an operating system that that covers all these different 4 aspects and completely automates the way these procedures are executed. So we have operators that just specify the intent. This is specified over a graphical interface. We have a set of SDKs that interface the user with the system, with the actual operating system. Then we convert that into a machine understandable intent. So we perform the conversion from natural language to structured language that a machine can process. And then we have developed an orchestrator and controller that what it does is goes into the AI catalog and maps the intent into the AI models you need, like accepts, RApps, dApps, determine where they should execute, if it's the near-real-time RIC, the no-real-time RIC, then packages the entire intent as a set of AI logic, services, and configuration files and policies that can be deployed. And then a few seconds later, the entire network gets reconfigured to satisfy the intent. So as a startup, that's the product that we are developing. And there are already deployments and pilots of this solution. And this is basically our core business. But to make this happen, we had to go through a variety of different challenges. And I'll go now and spend a lot of time, not a lot of time, but a decent amount of time on the challenges that we face, trying to cover what are the major ones, of course. The first thing, I will say that the biggest challenge, we are talking about RApps, accepts, and dApps. They have all different inference time requirements. No real-time RIC, you can take decisions anything higher than 1 second. So that's not a really strong requirement. But accepts, they have to take decision lower than in less than 1 second. dApps, it's even more stringent. You have 10 milliseconds to take action. So how do we ensure that this happens? So accepts, RApps, dApps, they are microservices. So they have containers, they run on general purpose servers. And the problem is that they will coexist with other accepts. So if you have a near-real-time RIC and you have a network with 1,000 base stations, you will likely have thousands or even more accepts controlling each individual base station or doing different things. And so this kind of like raised the question, can we really support these many accepts on the same compute node? And so what we did is we trained different AI models. In this case, I'm showing here, let me take the laser pointer. We trained, for example, CNNs, LSTMs, and deep reinforcement learning agents. And we said, okay, let's have these many accepts, like hundreds of them, executing at the same time in the near-real-time RIC. Can we keep and monitor the latency that on the inference task? So you see here, for example, for CNNs, for the architecture that we used, as soon as you start increasing the number of accepts on the same compute node, the same server, you see that there is a point where you start exceeding the inference time of the accept. You're actually entering the no real-time RIC region, meaning that the accept was supposed to take decisions in 1 second. It's now taking decisions higher than 1 second. We did the same for LSTM. This is even more evident. You see here, pretty much for CNN, for the CNN architecture we used, 100 it's kind of like close to the maximum limit for the near-real-time RIC region. But for LSTM, we reached that region much faster. And if you look at deep reinforcement learning, that region will reach that even faster. Just like a few 30 accepts at the same time, they already take decisions at a rate that's higher than 1 second. So what we did is basically kind of like trying to model this behavior. We extracted models and we did a lot of data collection. Then we created the models. We found out that actually you can use piecewise approximations to map the latency to the inference time. And then we use this to basically understand exactly where we should place accepts, how many servers we need, and if you want to save energy, what's the minimum number of servers that we need. And this is basically just trying to show you that placing the AI in the right place is fundamental, because if you place too many AI algorithms in the same node, then you basically have a run that is being optimized by agents that are taking decisions too slowly. Another challenge is, where do you place the intelligence? For example, do you want to, if you have the same network slicing model, do you use an dApp, do you use an XApp, do you use an AirApp? This is an important decision, because if you place the AI in a certain location, you're basically tying the AI to the input that is available at that location. And if the input is not available there, you need to have to send the input to that location. So if you're generating data at the CU and you want to execute, for example, the intelligence of the app, the data is there already. But if you're generating data at the CU, but you are executing everything as a no real-time wrap, then you have to take the data from the CU and send it to the wrap. And it will determine the introduced latency, introduce overhead on the interfaces. So you need to exactly understand, and this will impact the inference time. So you need to place this exactly and optimize the location of where you place the AI. Another challenge is related to distributing the intelligence. In this case, for example, imagine that we have two AI models. One is doing network slicing, the other one is controlling cell on-off. You can, for example, have the same two models executing in the same location. In this case, for example, as an error, as two AirApps in the Northeastern RIC, or you can distribute that as an AirApp and an XApp, or as an XApp and multiple versions of dApps. So which one is the right one? This depends specifically on the use case and what's the intent. And it depends on if certain loops need to happen at a certain speed. If you're controlling, for example, network slicing, you might want to adapt the RAN frequently and fast. So you might want that to be closer to the radio. If you're doing forecasting, for example, or if you're controlling cell on off, that's a decision that can take more time. So you're just fine with executing that as a no real-time RIC application, so as an AirApp. And also, how many resources do you have? Can you support this many applications in the same server, in the same brick? Those are all things that you need to consider. The other problem, which is very peculiar to Oren, is conflict management. So imagine you have two XApps. You have a max throughput and energy saving XApp. I guarantee you that they will fight each other. And here I'm showing just like an experimental results that we performed on our testbed. We have a throughput maximization XApp, which allocates pretty much a lot of resource blocks to, this is the number of resource blocks allocated to video streaming slice, EMBB. And then energy savings tries to allocate less resource blocks. If you run them all together at the same time, they start fighting each other. One says, no, we should use less PRBs. The other one says, no, we should use a lot of PRBs. And they will keep doing this forever. And this creates oscillations, which are not very good because performance will start oscillating. But the most important part is that no one is happy. So everyone is unhappy here because everyone is taking an action, then another one is counteracting that action, and no one is happy. So in this case, for example, what we did is creating a conflict management tool to understand exactly what are the applications and that you can deploy based on intent. For example, the pipeline is, I'll go very fast here, but a developer, let's say, that produces a new app, then you accept that they want to push to the marketplace. Operator needs to know how their XApp is controlling the network, because they need to know if their XApp, once deployed, will fight with other applications that are already in the network. So what we have the design, there are more details in the paper below, but you can, and this is a joint work with Deutsche Telecom. So you have a profiler, and the profiler will look at the XApp, will create a testing pipeline in parallel. In this case, we are using Colosseum, but you can use any digital twin, NS3, different emulators. So you test how the XApp will take decisions. You can create statistical profiles. So for each application, you create a statistical profile, then you add it to the catalog. Once the operator determines what are the applications that they want to deploy, they can go to the catalog, go look at the application profile, and then there is a whole pipeline that we have generated to detect when conflicts will happen, evaluate the conflict severity, because this is the most important part. Because what we realize is that in pretty much all cases, when you have to accept taking decisions, they will most likely generate a conflict. Now, the problem is the conflict severe, or is the conflict something we can just bypass and we don't have to necessarily be concerned about that? And this is what operators are concerned, the severity of the conflict. They don't care about if there is a conflict or if there is no conflict. They just need to know, will this conflict lose 30% of throughput? And this is basically how we design the system, creating a conflict report so that operators are aware of how severe is the conflict, and then they can use that to create conflict mitigation policies so that if the conflict is higher than a threshold, we prevent certain XApps or RApps or dApps from being deployed. And we create a set of applications that actually can be deployed. For example, here I'm showing in green, we have just like 5 different XApps. We can discuss later what exactly they are. But these different XApps, like the green ones, those are XApps you can deploy at the same time. The red ones are XApps that are generating a conflict that is too severe. So operators don't want to deploy them because, for example, they generate a latency increase of like 50% or the throughput decrease of 30%, which is unacceptable for them. So it also suggests what are the XApps you can deploy without even caring about what the conflict that it generates. And another problem is online training. So a lot of people say, okay, we train the AI, then we deploy that on the app catalog, and then operators will just deploy that, and then we do online training to customize the AI model to the deployments. This is great, ideally, but in practice, once you start generating online, when you start the online procedure, you see that the performance are very, very fluctuating. So in blue here, I'm showing the train model. The train model is fairly static, delivers performance that are fairly constant, so there is really no need to be concerned about fluctuations. But if you do online training, you start exploring. And once you start exploring, the AI needs to take decisions which might be bad. And even to gather knowledge that a certain action is bad, so we should not use it, it needs to test it. So if we start testing bad actions, users will be affected by that. So how do we improve this? One approach that we found that be extremely helpful is the use of explainable AI, because explainable AI can tie actions to certain performance indicators and can understand when AI will take certain actions. And we can create profiles that are kind of like safe, meaning that if we can profile the AI properly, we can identify what are the actions that the AI will take in advance, and we can determine if that action is not beneficial to the network. And we can shield the network from the action being taken. We can replace with baseline actions before the AI actually makes that decision. In this case, for example, at the bottom part, just focusing here to the left, this is the throughput that we will achieve when there is an XApp that is being executed. If you see, for example, the green line, which is a better line, what happens when we have the online training procedure in place, but we keep monitoring the AI agent. And every time the AI agent is taking actions because it's trying to explore that we know are not very good, we replace them with other actions which deliver a better performance, for example, in terms of throughput. Once we do this replacement, we can really improve the throughput even while the agent is learning. And then we can say to the agent, look, this action is not good, and we can give the agent a bad reward. And you have to compare the blue line with the green line. The blue line is where you just do online training as it is. So you keep the agent able to explore, but this exploration creates problem. When you still facilitate exploration, but limit the type of actions that the AI can take, you get better performance. And basically, we kind of like try to address all these different challenges using this orchestration framework. We call it orchestration. It's part of the operating system that we have developed, which kind of like covers all these aspects. In terms of logically, operators submit requests. So for example, I have this intent, so I need to have this certain functionality in a certain area. We collect the request, and then we convert that into a machine understandable profile. And then we have an orchestration engine that access the AI catalog, determine which model, where, and when to deploy them. We can deploy RApps, XApps, or dApps, and then we take care of the deployment. The deployment, of course, leverages ORAN interfaces like the O1 interface. You keep monitoring the performance of the network using the E2, for example. And so it's kind of like trying to cover the entire loop. And I'll stop here. And probably I can hand it over to is Pedram?
Yes,
I'm here.
All right. And I'll hand it over to Pedram, and then we can have time for questions later on.
Wonderful. Thanks, Salvo. Hi, everybody. This is Pedram Johari, a principal research scientist at Northeastern University, the Institute for Wireless Internet of Things. I'm going to try to share my slides. Let's see. you guys can let me know if you can see the slides in the presentation mode.
Yep.
Yes.
Wonderful. Okay. This is the work that I'm going to present, and I'm trying to keep it short to just give the people who attended this seminar to be able to, have a little Q&A towards the end. I'm going to talk a little bit about the wireless digital twins and primarily the work that we have been doing in the past 3 or 4 years at Northeastern University, where we host the world largest wireless network emulator, Colosseum. I'm sure that Michele and Salvatore has done a great job in explaining some of the applications that this wireless testbed platform enables. But I'm going to talk a little bit more on the lower layers and how we create digital environments with a high fidelity compared to what happens in real world. Very briefly here, Colosseum is a data center. Today we call it the Open RAN Digital Twin. It has 25 racks of servers and radios. As of today, it's around 170 or 80 computers, 256 software-defined radios. Those are all provided by NI, X310 USRPs. We have a fabric of FPGAs that will take care of the channel emulation of the system. And then we have a profile portfolio of NVIDIA DGX GPUs that helps with all the AI capabilities in terms of training and inference that I'm sure, again, you have seen some of those applications in Salvatore's and Michele's slides. Not going through all the details, but what it has essentially, we have standard radio nodes that has a computer node and a software-defined radio, and you can pretty much program it to any type of protocol stack that you want to use. These days, we are primarily using the open air interface with the Open RAN protocol stack, but that does not prevent the users to use other technologies if they have interest to use them, including Wi-Fi, Bluetooth, LoRa, and others. And again, the channel emulation happens in what we call it the massive channel emulator. What I'm going to talk about today is going to be focusing on the channel emulation part, and that's where we essentially create the digital twins. The main part of this work, as of a year ago, has been supported by a grant that we received through the Public Wireless Innovation Funds from NTIA. The project is called DigiRAN, that's Digital Twins for Open Radio Access Networks. And what it has is essentially 4 thrusts that you can see them in 4 different colors. The main one, or let's say that the building block is the blue block on top right of this picture. That's where we create digital versions of the real world. I'm going to talk a little bit about how we do that and where we are in terms of creating them in an agile way. It's essentially using 3D building maps and ray tracing software to create digital twins and then deploy them on Colosseum that does the channel emulation. The other part of it on the left side in the middle it's what we call it the networked twins, and we have a publication on that will be presented in IEEE GlobeCom later this week. That's called TwinNet. That's a live link between what happens again in a deployed network in real world and in an emulated network, which in this case we are using Colosseum. So that creates a link between the 2 worlds, if you will, and they can talk back and forth and sending information. And the green boxes down here is essentially a user interface that helps the users to log into the system. And then part of the yellow box that I just talked about has an MQTT subscriber and broker sitting on the real world and the digital world. And that facilitates the interactions between the 2 platforms and also giving access to the user so that they have visibility in terms of what's happening in their emulation system. And then bottom right, we have this concept of bringing your own device. That's the integration of different components of the Open RAN, including the radio units that requires their own hardware, and then DU and CU, which will reside on the same servers that we have on Colosseum, But again, this is customizable with different solutions. And then on the side of it, of course, the RAN intelligent controllers that again, Salvatore was just mentioning some examples of that. That's supported again for the training phase. We have GPUs, powerful GPUs, and then for the inference, the servers that we use for the different components, they usually have enough power to run the AI applications. That being said, I'm going to take a few minutes here on explaining a tool set that we created 2 years ago that's called CAST. I have the reference of that paper if audience are interested to look into the details. But what it does, essentially the blue box at the center that you see here, it creates digital twins and it will do a sounding or validation phase. So it closes the loop. What happens is you can feed this tool with any scenario that you have in your mind, including mobility of the nodes, and it can be outdoor or indoor. For outdoor, it's going to be the 3D map of the buildings. For indoor, as you can see an example at the bottom left, it can be again a 3D map of the indoor environment. And we have done this practice in one of our over-the-air testbed platforms called Arena at Boston campus. What it does essentially, it takes that information, it takes the location of the nodes, whether it be G node Bs or UEs, and then it will do the ray tracing and create the digital scenarios. And on the sounding, that's the normal practice of channel sounding that happens over the air. This is just happening on an emulation system. And it will essentially gives you the feeling that you have created your digital twins by preserving the accuracy of the channels. I'm not going to go through all the process because I know we are short in time, and I have probably a couple more minutes. Again, the steps and everything that you need to create arbitrary scenarios, you can find them in this reference paper here, and we'll be more than happy to share it with the organizers and they can send it to the audience. We are at the stage that we can create customized scenarios for users based on their interest. And we'll be happy to chat about that. I'm going to skip a few slides. This is just an example of an outdoor environment with a CV2X scenario. That's a couple of OBUs, onboard units, and a base station, and with mobility of the nodes that we have created for a collaboration that we had with the Department of Transportation. That's just one sample scenario to show you how the process works. Again, in the interest of time, I'm going to skip this slide as well. But in general, what it does is this is a normal practice of channel sounding, sending pseudo-random codes, receiving them, doing the correlation, and figuring out the channel impulse response that the channel emulator is producing for you, and comparing that with what you are feeding it with. Very quick here, these are the comparisons between what happens in the simulation or real world compared to what happens in the channel emulation. We have been able to show that within a few dBs of error, margin of error, we can emulate any type of scenarios, including indoor and outdoor with mobility on Colosseum. Again, given that Michele probably has already talked about CI/CD, we have a platform and a pipeline to create and deploy new versions of the code on our emulation platform. This complements the physical layer digital twinning. So we create the environments, and on top of that, we can also duplicate or replicate what happens on the latest version of the protocol stack, and then we'll deploy that. We have an automated system that will deploy that on our emulation system, and we can benchmark and essentially test in terms of again, a couple of examples. This is our Arena system. This is a comparison. The graphs that you see is a comparison between what happens in over-the-air platforms versus Colosseum, which is an emulated environment. And as you can see, again, within a couple of dBs of error, we will be able to replicate those scenarios. What you see at the bottom right is a jamming scenario when we are sending on the left a narrow band jamming signal, and on the right a wide band jamming signal. Blue and orange curves are showing you the simulated versus the emulated versus the actual over the air results. And as you can see, they follow the exact same pattern on both. Let's skip this one. I'm going to show you only one short video of a demo of what we have been able to achieve. Again, we have a ray tracing software that can do ray tracing within 30 milliseconds with a very high accuracy compared to state-of-the-art software out there, including Wireless Insight. The fast ray tracing on Wireless Insight will generate a 20 dB error. With the AI model that we have here within the 5 dB margin error. I'm going to skip this video, but I will show you the next one. And I will conclude here so that we can open up the Q&A for the people. But what you see here is the latest version of what we have on Colosseum. 3-4 years ago, Colosseum was able to only we were only able to create off. Then you didn't have any control over what's happening in that scenario. But today we have a dynamic scenario generator and creator, which I did not go through the details of how we have enabled this. But what you see here on the right, there's a GUI with a map with a distribution of 3 UEs at this example and 1 base station. And when I play the video, you will see that in real time, everything is happening with a refresh rate of 1 millisecond. So in real time, I can drag and drop the location of the UEs. And of course, I'm sure that you can imagine this can be integrated with an automated, mobile scenario generator, including some of the simulators. For example, we have tried it with Sumo for vehicular communications. So essentially what is happening here in real time, I can drag and drop and choose a new location for the UEs. And then on the left side, in real time, again, in that data center that I just talked about, Colosseum, everything is being emulated with real radios, and you can bring your own commercial radio, RUDU and CU. And then it will generate some KPIs for you. The applications are numerous. I would name a few. Some of the companies operators are interested in doing site planning and site optimization. This is going to be a great tool for them that they can test everything with their radios. On the testing itself, testing equipment companies are also interested in creating emulated based high fidelity testing equipment that you can hook it up with your hardware and then generate any type of scenario virtually and then create that in your digital twin. I'm gonna stop here again in the interest of time so that we have a few minutes for Q&A. I will be happy to take any questions.
All right. I think we have some questions from the Q&A box. Maybe I'll just start and I'll take the question from Oluwason, which was sent first. And the question is, are there open platform to experiment AI in Open RAN? And the answer is in part yes and in part no, in the sense that, for example, what Pedram has just presented, the Colosseum testbed is a resource that is open to the research community, has some AI resources, and that you can use to train AI and ML solution on top of these networks. But at the same time, AI is growing and growing. Now you have these Gen AI applications that require a lot of training power, and then you have for example, algorithms which are more complex to train and so on. So I would say there can be more, there's more that can be done in terms of test beds for AI and wireless, and while something is there already. And I hope this addressed the question. Please feel free to follow up in case. Ben, I think there's a couple of questions for Salvatore.
Yep.
If you want to take them, Salvo.
Yeah, I can start with the first one. I see the first one was from Fabian. The question is, how do you handle trade-offs in intent specifications that you get from operators? And the follow-up seems to be related to challenge for conflict management. Yes, that is a very good question. And yes, you're correct. So there are many problems that are related to intents that are generated by operators. Most of the time, the intents are themselves conflicting, even just a single intent. Like operators asking, I want to deliver the highest throughput, but I also want to save energy, which is kind of like inherently conflicting intent with each other. So the way we process different intents from multiple operators or from the same operators, which kind of like submits multiple intents, the framework that we have developed for the conflict management allows operator to specify also what's the priority for each intent. Certain intents might come with a lower priority than others. For example, to satisfy service level agreements, they might give priority to satisfy a minimum throughput requirement and give less priority to saving energy. That priority index is embedded in the conflict mitigation policy so that the system knows that certain intents have a higher priority, and when kind of like providing the output saying that a certain application should not be deployed because it creates too high of a conflict, that decisions accounts for priorities, and only applications that it intends with a higher priority will be deployed. And then if there is room for adding new apps with lower priority, they will be added, but the system will prevent from kind of like violating intents with a higher priority, or at least with a weight that is higher than the other ones. And so this is the way that we are processing intents at the moment, is considering like the conflict and how the intents will impact performance. And at the moment, the preference is being expressed by the operator itself. So the framework is agnostic. It can prioritize any intent over another one. But operators need to specify what's the priority of their intents. And I see that Fabian had a follow-up. Thank you. So kind of force them to be more precise by setting priorities. Yes, that's correct. That's the because the system doesn't have any knowledge about what a better intent. It's operator that needs to specify that. And unless there is any follow-up on this one, I'll probably move to the other one, which is from Andre. Which is asking how to mitigate various inferences of AI. AI inference has stochastic nature. This is another very good point. So in general, what is happening is that in Oran, I will say that there are two different ways AI inference happens. One is the so-called event-based, and the other one is called periodic. So for periodic AI inference, this is very predictable because, for example, the AI will receive KPMs every, let's say, 200 milliseconds and will take a decision. So this is extremely predictable, and it's something that we can easily model. In the case of trigger-based, AI inference only happens when there is a certain event. For example, we experience a performance drop that is of like 10%. So in order to kind of like model that specific phenomena, what you can do is doing data collection, looking at the distribution of the inference times for the AI, specifically for the trigger events. So you can determine exactly when a trigger can happen. You can get the PDF, for example, for that event to happen. You can embed that knowledge into the inference time modeling. So you can have different you can basically integrate the decision, the inference time, and you can integrate the modeling of the trigger event so that you can determine what the inference looks like based on the probability that a certain event will be triggered. You can integrate that into the model. For the results that I shown, this was not considered. We just look at the data. So we didn't model directly the inference, the triggering event. But we extracted these using AI directly from the data. I don't know if that answered your question. Please be able, just like, feel free to follow up on the question. And if there is no follow-up, I think that the other question probably is maybe more related to Pedram.
And the question specifically is, what is the procedure for using the testbeds? Is there any free trial for Colosseum?
Yes. As of today, we provide access to all the US-based universities who have active grants from NSF or Department of Defense. That being said, in general, with other academic users, if there's an interest and if there's a project that you want to work on that is perfectly aligned with the goals of Colosseum, we can give you trial access to try things. If you go to colosseum.net, that's our website, and if you scroll down, you will find a form that's called request for a team. It's a very basic form. Just put it in, reach out to us. Again, the requirement is having US-based funding, but again, reach out to us with the specific need, and we'll be able to help you with that.
All right, and I think with this we answered the questions in the Q&A box. Is there any other question, doubts, curiosity? All right, then maybe we can give it back to Matt.
Yeah, sounds great. So thank the panelists very much for this wonderful and amazing discussion, highly educational. We're going to have a recording of the session put up on YouTube. It's going to be linked off of our main webpage if you want to view it later, share it with your friends. This conversation will continue on the Slack. There's a link posted in the chat if you would like to continue interacting with the speakers. They would love to, continue talking with you, answering questions. Please feel free to join. In 2 weeks, we're going to have our next special event. It's going to be a fireside chat with Amin Vadat, hosted by Nick McCune, on the topic of networking in the area of warehouse communications and artificial intelligence. So thank you very much.
Thanks.
Thank you. Bye-bye.
Bye, everyone.